Dear students, today through this video we are going to revise the concepts that we have learned from mechanics of solids regarding supports and support conditions. Along with that, we will also see how we can calculate strain energy for beams subjected to bending moments. So first we are going to start with the supports. So we are very familiar with basically four kinds of support conditions, mainly fixed, hinge, roller, and the other one is free. Okay, free. These are the very common four support conditions. And when we hear about supports are basically some images associated with boundary conditions. When we see this particular image, we will understand that it's a hinge support, which basically talks about a boundary condition. Boundary condition is actually the restricted or released movements for a given joint or a node. When you go through higher versions of structural analysis like SA2 and SA3 and all, you will be calling joints as nodes. So here what you can find is this is a joint, and this joint represents these different conditions, and I'm naming the joint as A. So when we hear about these things, there are two things that we are bothered about. One are the releases and the other one is the restrictions. Okay, these are the two things that we need to take care of. And we should know that whenever a movement or a motion is restricted, reaction develops. A very simple example what I can tell you is that if on a Friday morning a new movie got released in the nearest movie theater, so the students in the class is asking me, "Sir, can we go for the movie?" If I say no, reaction develops. I restricted the motion and reaction developed. If instead of that, if I had said, okay, you can go, there won't be any reaction. Similarly, whatever movement is restricted, there all you are going to get reactions. For example, if you are considering a fixed support denotes a boundary condition in which the horizontal translation, vertical translation or horizontal and vertical movements, and also the rotations are restricted. Okay, all these things are restricted. So no translation or rotation is allowed or released. Everything is restricted. And in the restriction, you are going to find all these things. Okay, that is the case of a fixed support. When you are considering hinge, it is more like the hinge of a door. So you know that a door, you can actually freely, if this is a door, okay, this can move like this, but you cannot pull it out, okay, it won't go, or you cannot make it move like this. The only allowed motion is this rotation. So if it is a hinge, the released ones are, okay, among these three, the one which is restricted or released is only the rotation, which means this and this are restricted. So here you are going to find among the restriction, these two are the restrictions. And when we are considering a roller, okay, it is more like a tire of a vehicle. Okay, so basically what we can see is that among the three, the vertical movement is restricted and the horizontal movement. So if you are considering a vehicle, the vehicle can freely move in the horizontal direction and it can freely rotate. So these two are allowed and this is restricted. So among the restriction, you are going to find only this. And in case of a free support, which means the boundary condition says that a free end of a cantilever beam, okay, for example, so it can move in all the directions, everything is released and there is nothing in the restriction zone. Okay, so this is basically what is meant by the different support conditions. So when we get problems for analyzing beams, the support conditions will be given in the problem. So you should be able to convert a given beam into these reaction components. Okay, for the best example what I can tell you is that, say if you are having a simply supported beam, okay, which means a beam that is having hinge at one end and roller at the other end. So if you want to represent it in terms of reactions, it can be represented as, this is a hinge, which means that the vertical and horizontal translations are restricted. So you are going to find reactions. Okay, you are not going to have a moment here because the rotation is not restricted. Whatever that is restricted will be getting converted as reactions. This is a roller, okay, and in the roller you know that only restriction is in the vertical movement, so you are going to have only one reaction. Similarly, if you are considering a cantilever beam, okay, when you are considering a cantilever beam, you can see that this is fixed end. In the fixed end, all these three are the restrictions, which means you are going to have three reactions. Okay, you'll be having three reactions here, and this is the free end, and the free end there is no restrictions, hence no reaction. Okay, we'll go for a higher case. Say I'm having a beam like this. There is a roller here, another roller, and this is fixed. So if I want to represent this as reactions, the diagram will be something like this. This is a hinge, which means two reactions. This is a roller, one. This is a roller, one. Roller, one. This is fixed, which means I'm going to have three. So this is the representation of a continuous beam. Okay. So this is how we convert these images into reactions. This is highly needed when we are trying to solve problems. Okay, so this forms the first part of the lecture. In the second part, what we are going to see is the case of the calculation of strain energy. That is a concept that we got introduced in the second module. In the last lecture also we talked about strain energy, and we have the general equation for calculating strain energy for a member subjected to a flexural load or a bending moment is given by U equal to integral m square dx by 2ei. Okay, so this is the expression that we are going to use in the second part of this video. So this is the second part. So we have this one, and so we are going to consider a simple case. Okay, a simple case, which means the most simple case is a cantilever beam. Okay, a cantilever beam subjected to, say, a point load. Okay, subjected to a point load W at the free end, and let the physical properties of this beam be L and I, and the material property be E. Okay, so these are the different parameters, and let's name this beam as beam AB. Now, when we think about constructing this particular equation, that is U equal to integral m square dx by 2ei, there are certain things that you need to concentrate on. So the easiest way to approach this problem is to approach in a way where you can have it in a tabular column, and the tabular column will contain different values starting from, okay, I'm giving the table here, starting from the first one is S represent segments, E represents elasticity or flexural rigidity, then I have L, which represents the length or limit, then O, which represents the origin, and finally I have M. So when you consider doing a problem, to solve a problem or to calculate strain energy, these are the things that you need to have. So this is, to remember this, what I used to do is that I used to represent this in the reverse order. When I look into the reverse order, it says the term moles. Okay, if all these parameters are correctly represented in the table, then the calculation part is very easy. Now I will show you how to do it. Okay, so this is how the table is going to be. So now we'll see one by one. The first one says segments. Segments means if you have a beam, okay, it can be a cantilever beam, simply supported beam, or a continuous beam. So segments, a beam will be divided into segments by point loads. Okay, when we say point load, Do not consider that, so in the first thing that is going to come to your mind is that when I say point load, this will be the picture that will be having in your mind. Okay, say 10 kilonewton or something will be, you'll be considering it as a point load. Actually, there are 2 point loads. This is point load. This is also a point load. Okay, point load basically means that any load that is acting or concentrated at a point is called as a point load. Okay, so when we want to divide something into segments, okay, when we want to divide something into segments, the basic thing what we require is to look for these point loads. These can be either external loads or it can be the reactions. Okay, so I'm starting with this, the first one that is available here. So it's basically tells that each location of point load should be dividing it into different segments. For here you can see there are just these 2 points, so this can be handled as a single segment. Okay, here also there is 1 point here, another point here, a single segment. But when you consider this one, how many segments will be required? So you can see here there are 2 point loads, so this can be called as segment 1, segment 2, segment 3, segment 4. So this is how we divide the different beams into different segments. So I will give you another example. Consider a beam. Okay, say this is fixed end and I'm having a support here and another support here. Okay, and let this be free. There is a point load, say 5 Newton, and there is a moment 10 kilonewton meter. Okay, so let it be something like this. So when you have this, you need to look for this version. Okay, the best easiest way is to have this beam in this version. So what will be this beam? So this beam you can represent like this. Okay, you will be having, this is a fixed end, so we'll be having 3 reactions to the max, and here, okay, this, and apart from this we are having our external load, that is 1 here and 1 here. So now you can see there are different point loads. So how many segments this should be divided into? So you can see that the first segment should be this part is the first segment, and here you have the second segment between these 2 point loads. Between these 2 point loads you will be having third segment. Between these 2 you are going to have fourth segment, and between these 2 you are having the fifth segment. So this is how we divide a given beam into segment depending upon the support condition and also the given external loads. Okay, so that's what this segment part is, and E represents basically the EI value. Okay, the flexural rigidity. So if in this case we can see that there is only 1 segment required. Okay, so here you can see that there is only 1 segment required, and the segment is having, this is the segment, constant EI. Throughout the segment the value of E and I is constant, so I can write it as EI. And the next one is for limits. What is the limit? So this segment having a limit of 0 to L. Okay, so now there is a tricky thing where we should decide the origin. This represents the origin. Okay, so the length I know it is L, so this is 0 to L, and I need to decide which one should be 0. I can take this one as 0 and I can take this one as 0, both are fine. But whenever we are dealing with a cantilever, considering the free end as the origin is an easier approach to solve the problem. So here I am considering B as the origin. Now I need to think about moment. Okay, this M represents the bending moment, the expression for bending moment. To get that, what you need to do is, in each segment, now we are dealing with segment 1. So if you are dealing with segment 1, just take a section at a distance of X from the origin. You need to be very careful, the distance should be from the origin. Here B has been considered as the origin, so this distance represents the X. Okay, so this distance represents the X, and this XM is basically mx, okay, where this is the section xx. So you are calculating the moment at this section that you are considering. So here you can find that the load is W, the lever arm is X, so it's going to be Wx, which is going to be the moment value. So the value or the magnitude is W times X, and I need to check whether it is a sagging moment or a hogging moment. Here you can find it is a hogging moment, hence I am giving the value minus Wx. Hogging moments are negative and sagging moments are positive. Okay, so we have all these conditions. Now you simply substitute these conditions in here to get the strain energy. Okay, so let's calculate that. We'll calculate here itself. There are some space left in this page itself. We'll go with that. So I'm going to calculate U is integral. Okay, and what should be the limit? 0 to L. M square. M is minus Wx, so M square is going to be W square X square. Okay, square of negative becomes positive. Dx, EI is EI itself, so I can directly substitute EI itself. So I have this condition. Once I do this integration, I'm going to get this W square by 2 EI is constant. I'm taking it outside. Okay, integral X square is x cubed by 3 in the limit 0 to L. I directly have the answer. W square, if I substitute the limit, it's going to be W square L cubed by 6 EI, which is the strain energy of this cantilever beam subjected to a point load at the free end. So it is very easy to calculate the strain energy if we are comfortable in writing the moles. Okay, segment, flexural rigidity, limit, origin, and the moment value.